We've seen that there are some triangles that we cannot use the law of sines to solve because we don't know a side and an angle across from it. And so we need to come up with another uh, tool in our tool belt, another thing that we can go to besides the law of sines that will help us with triangles like a side triangle if we know all three sides, side, or a side angle side. Those were the two that we said should be solvable, but are not solvable by the law of sines. And so we're going to see another way that we can tackle these kinds of triangles. All right, so I've got a triangle here, ABC, and remember that the way we name the sides is with the same letters, just lowercase, and we keep the sides across from the angles. So if this is angle A, we'll call this little a. Here's little b down here, and little c over there. Well, what we're going to do is very similar to what we did to come up with the law of sines. I'm going to put in an altitude that comes from angle B down to hit side B. What I've done is I've put in a new line. Let's give that a name. We'll call it H. We've also split side B into two pieces. There's a piece over here that we'll call, we'll call something, and this piece over here we'll call something else. Let's see, I'm going to call this one on the right-hand side here X. And since the entire thing is B, and this is X here, then what's left over would just be B minus X. I take the entire length and I subtract off the X, so what's left goes over here. Then this is B minus X. And because I drew this line in at a right angle, I've got two right triangles, which means I can apply SOHCAHTOA, and I can also apply the Pythagorean theorem. We're going to do the Pythagorean theorem for both triangles, and we're only going to worry about the SOHCAHTOA for one of them. So let's do the Pythagorean theorem for this right-hand triangle first. Over here, A is the hypotenuse, so we've got h squared plus x squared equals a squared. In the right-hand triangle over here, C is the hypotenuse, so we've got h squared plus b minus x, the whole thing squared, equals c squared. Before we move on, I'd like to get rid of the parentheses on this. A easy mistake to make, it's so tempting, is to say that b minus x quantity squared is the same thing as b squared minus x squared, but that's not the case. If you multiply the two binomials, b minus x times b minus x, there's extra terms in the middle. We get h squared plus, when we do b minus x times b minus x, because that's what squared means, is I'm multiplying it by itself, we get that b squared. We do get an x squared, but it turns out to be positive because it's negative x times negative x. And we also get a b times a negative x and another b times a negative x, so we get negative 2bx. Okay, so that's what b minus x quantity squared FOILs out to be, and then that equals c squared. We also have over here in this triangle, I'm going to use SOHCAHTOA on this, and I'm going to say that the cosine of angle C is equal to x over a. We could do that over here with this triangle too. We could talk about the cosine of angle A, but I don't want to because this is going to be enough. So I've got cosine of C equals x over a. We'll multiply both sides of this by a, and little a times the cosine of angle C is equal to x. All right, so we've got three equations here that we are going to combine. The first thing we're going to do is we're going to take the two Pythagorean theorem equations, and I'm going to rewrite this bottom one, but I'm just going to rearrange the terms. So I've got an h squared. These three terms, I'm just going to put them in a different order. I'm going to put the x squared first, and then the b squared, and then the 2bx. So it's a positive x squared, so I've got plus x squared. It's a positive b squared, so I'll put plus b squared. And a minus 2bx, so that's minus 2bx, equals c squared. Now, what we're going to do is we're going to say, hey, look at this. That h squared plus x squared, according to this first Pythagorean theorem equation, h squared plus x squared is a squared. So we can replace this whole thing with a squared. That makes our equation a squared plus b squared minus 2bx equals c squared. Now we're going to bring this one into play. We're going to say, hey, look, I've got an x right here, and I know what x equals. It equals a times the cosine of c. So if I replace that x with what I know it's equal to, I get a squared plus b squared minus 2b times a times the cosine of c. Just to put them in alphabetical order, I'm going to put the a before the b, but it really doesn't matter. It's multiplication. It doesn't matter what order you put them in. 2 times a times b times the cosine of c equals c squared. That equation right there is going to be our finished product. This equation right here is a lot like the law of sines, but hey, it doesn't have a sine in it. It's got a cosine, so we're going to call this the law of cosines. It doesn't look like the law of sines, but it's going to be useful in the same way that the law of sines is. It will allow us to solve triangles if we know three pieces of that triangle. Notice there are four things in here. There's a side, there's another side, A and B, we've already counted those. There's an angle, angle C, and there's a remaining side. There's three sides and one angle in this equation. If we know all three sides, then we can find an angle. If we know two sides and an angle, then we can find the remaining side. The law of cosines lets us do side, 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 or side, angle, side triangles. Let's see one real quick, and we'll try one like this. I know that in this triangle, this length is 4 units long, this length is 6 units long, and this is a 30-degree angle. I don't know what this is, but if we think of it as A, B, and C, we could say this is our angle C, which would make this little c, and then the other two can be little a and little b. It doesn't matter which one we call which. Let's call this little a and this little b, and so now our equation becomes a squared plus b squared minus 2 times a times b times the cosine of angle C is going to equal c squared. If we pop up a calculator here real quick, make sure I'm in degrees mode. I'm not, so let me make that switch real quick. There we go. So if I say 4 squared plus 6 squared minus 2 times 4 times 6 times the cosine of 30 degrees. I get that number, 10.43, etc. That is this whole side of the equation. That b there is a 6. I didn't notice it. That b there is supposed to be a 6. And maybe it is a 6 that just looks a lot like a b. That's c squared, so in order to find out c, I'll just take the square root of it, and c ends up being 3.23 units long. There's the law of cosines in action. We can do the same thing if we know a, b, and c. We can solve it to find angle c. Notice one last thing here, that if this term wasn't there, it would just be a squared plus b squared equals c squared. That's just the Pythagorean theorem. This is just the Pythagorean theorem with one extra little term thrown in. So really all you need to remember is the minus 2ab cosine c, and you've got the law of cosines down.